Okay. So in the case of alkenes, we're going to replace alkane with alkenes. So again, you're going to count the longest carbon chain, right? And you want to try to get the longest carbon chain. Now, we have a case here, right? At this very bottom case. Now, this is questionable. And I think I said that the last time, is that I wanted to stop here because this part is a little questionable. Let me pull up my pen. Okay, so if we count our longest carbon chain, so that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, the longest carbon chain does not include the double bond. For simplicity for ourselves, and also in organic chemistry, you want to try to include that double bond in that carbon chain, if you can, even though it's not the longest, which is one of the things that I hate. And the problem is that the IUPAC nomenclature has been modified over the years so that it will actually take the shorter chain and they would use the side chain, right? But then they would call this guy, they would use an ene. So this would be methene. No. So they'll use the YNE to represent the side chain, okay? So then that's an M. Okay, that EYNYL, because you remember, like methyl, right? So if it's just YL, it's understood not to be a double bond. It's understood just to be a single bond, right? All those are single bond if we're just using the YL. But if we use the EN, that means it's a double bond on the side chain. You understand? Okay, so they've started to adopt this as well. But we still have a lot of people that are going to use this as being the longest chain, okay? Because it has a higher functional group. And so you want the highest functional group with the longest chain to make it easier for ourselves, okay? Okay, so are you guys with me? Okay. Yes. Mm-hmm. It's in the side chain. In the side chain, yes, or in what they call it the substituent, right? The side chain, yes. Or they call it branching chains. Okay. Okay, so you guys remember EZ or cis trans, right? EZ dealing with priority cis trans, right? Dealing with highest priority EZ, right? Then cis trans dealing with their comparable. So cis trans, oops. Okay, now here's the thing, right? So with the single bonds, we were able to get twisting to occur, right? With the double bonds, there's no twisting, they're locked in. You guys did the models the last time, right? Remember when you guys made a double bond, it was actually locked in, right? So you can't get that twisting to occur. You're stuck, right? So there's no twisting that's going to happen. So in this case, cis trans are going to be a lot easier in this context because you no longer have twisting, and so you don't have to deal with that aspects of things. Okay, so if there are two double bonds, right, we use diene, right? If there's three double bonds, we use triene. If there's four double bonds, we use tetraene. Say it louder, say it loud and proud. Okay, so no. Yes. Yes. Yeah. So no, you do pay attention to where your hydrogens are located. Like, but you also want to pay attention to priority, right? So like for instance, these guys have higher priority. The higher priority is on the same side, right? If everything's a hydrogen, then you don't care what the hydrogens are. But if they differ, you know, and so, but if you have three different moieties, you also have to pay attention. You may have a hydrogen, but you want to look at the priority, highest priority. If the two highest priority are on the same side, then it's, and then if they're across from each other, it's trans, right? So you are looking at the hydrogens, but you're really looking at, look on the other side. So it's, these guys have priority over the hydrogens. The hydrogens are cis to each other, right? In this case, but the hydrogens are trans to each other. But then that means because there's four moieties that we're looking at, then, right? So if your hydrogens, two hydrogens on the same side, of course, your higher priority is going to be. So do you understand what I'm saying? So you're getting bogged down with details that are not. Yes, but even for Z and E, right, it's the same concept, right? Because if you looked at your hydrogens, right? Yeah, but even with system trans, it's also priority. If your two most important things are on the same side, then is it going to be cis or trans? Yeah, yeah. I mean, yeah, so you can look at the hydrogens, but you don't have to look at the hydrogens. Do you know what I'm saying? So it's perspective. So that individual chose the hydrogen, like this book. If you notice what they're highlighting, it's the hydrogens, right? It's a perspective, right? So it means the same concept. Do you get a different concept if you look at the ones that have higher priority? You still get the same concept, same answer, right? Yeah. So it's just perspective. Like I said, so one author likes to say, oh, it's easier to look at the hydrogens, and if that makes it easier for you, then look at the hydrogens. But it's just as easy as to look at the ones that have priority, right? That's right. Yeah. That's right. It could be two methyl groups, right? But then you have to look at priority in that case, right? And so, but then in that context, if there's two other methyl groups, then that could be cis, right? In this case, you can use either cis or Z. Yeah. It really doesn't matter. Like I said, Z is Z and E are based solely on priority, right? Yeah. No. You can't have trans E and no. You're going to either have one or the other. Yeah. And if you ask me which one is IUPAC nomenclature, they're both IUPAC nomenclature. That was the next question, right? Which one is common and which one is IUPAC? Okay, does that help? Okay. It's so funny because you guys ask a lot of interesting questions. So, double bond, right? I'm going to put, okay. So, let's see. And I'm trying to remember all of the ones that we've gone through. Yep.
So the way to differentiate this part from the ENYL would be we would use the ENYL when talking about the side chains and this when we're talking about the four chains. I don't know, like using the DIEN into like your meaning.
Okay.
It's like bothering me because I'm like, I know.
Okay, so let me explain the D, I, E, and E, right? Okay, so yeah, you could have D, I, and E into your side chains as right? If you have two double bonds, so this just tells me I have two double bonds, right? This tells me where the two double bonds are located, right? So I have one on the second that starts at the second carbon and one that starts on the fourth carbon. There's my first, second, third, fourth, fifth. So it starts on the second carbon and ends on the third carbon. So that's why I put the 2 there. It starts on the fourth carbon. That's why I put the 4 there. So that tells me where the two double bonds are at. Okay. Now, the thing is that when you have this, now this is one way of writing it. The other way of writing it is this way. And I'll tell you the reason why they write it both ways. It's hep. Oops. If I could spell. Hepta. 2, 4, 9. Okay, so when you start having things in front of it, side chains, it makes it a lot more complicated, right? So what they'll start doing, or if you have multiple structures in here, right? Let's say you had it was an ether, right? So if it was an ether, right, you would use an oxo, right? Or I'm sorry, an oxy, OXY, right? So we'd use something oxy, blah, 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 right? It makes it a lot harder in that context. Because of that, they'll often do it like this as well too, to tell you that this refers only to the double bond, because you could have in that main chain, you could have an alcohol, you could have a double bond and things as well too. And so you would use that di-ene, right? And put the numbers here. Do you guys see that? Jessica? Yeah, okay. So you'll see it written both ways. So this tells me, okay, everything else is single chain, but this here, we have a double bond on the second and the fourth carbon. Okay. Main chain, yes. So if it's integrated into the main chain, it has to be in there. So like sometimes if you have a double bond and a triple bond, right? So we'll use YN, right? And we'll say where that YN is located, and we could end up having a double bond too. And I'll show you that here in a second. Okay. Yes. Because there's single bonds here. This is a single bond. This here is a double bond between the 2 and the 3, right? So the double bond starts, this tells us where the double bond starts. It starts at the 2 and it starts at the 4. But that's a single bond between them. No? Yeah. So, okay. So here, what would you guys name this guy? Now, just give me the name. Don't worry about the cis and the trans. We'll get into that. Okay, so we'll start over here then. Yes, ma'am. Which way is this way? Okay, so let me see. So you're saying right here or right here? Okay. Okay, so I don't know. You tell me. So you're saying 1, 2, 3, 4, 5. Okay. So you said 3, 4, dimethyl. Okay. 1, 2, oops, 1. Okay. That would be correct. Is there another way of doing it? Okay. Okay. Simple. Double bond has priority over single bonds, yes. Or it depends on what the side chain is. So if it's a single side chain, yes. Okay. If it has a functional group like an alcohol or anything like that, it has less priority. Alcohol has a priority, and we'll talk about that. That's why I kind of hate the way that they're introducing the topic. How they're doing it. Yeah, it is. I'm learning the book still, so. Okay, so are you guys, you see how it works? Okay, so, but then there's aspects of this because this is a cis trans structure. Trans. Are you sure it's not a, look at that, are you sure it's not a? Is it a cis or a trans? Yeah, and they're both priority, right? Well, one is part of the main chain, right? One is a side chain. So if you look at the side chain, they're trans to each other. Trans, right? Opposite side chain, right?
So we don't look at the main chain.
Yeah. So if we count this as the main chain, but the problem is that you're right. In a sense, we can count this as the main chain, or we could account this one as the main chain. Right? So it just depends. Yeah. In this case, I wouldn't add it on there because either way, if you count this one as the main chain right here, then this guy would be, because that means your function, this would be a side chain, this would be a side chain, right? So then that would be cis, right? And then if I counted this as the main chain, then that would be trans, right? They're opposites of each other. Okay. So it just depends on how you count the chains, whether you would call it cis or trans. So does that make sense? Yeah, either one you can get it correct depending on how you number your main chain. If you don't number your main chain, then you screwed yourself, right?
No, like let's say like we didn't number them, but we guessed.
Then I would mark you off because you guessed, and then you didn't tell me. Well, but then I also didn't know that you didn't number them. I know that you didn't number them because I see you didn't number them. So then I would assume that you guessed, right? Yeah. You should on written nomenclature. You should number. That's different. Well, to see, because I can't test you on Chem 101. I mean, but I could test you when you have short answers. Maybe. Yeah. Yes, it is. Maybe. I may add another question on there now, since I know that you guys are not numbering. Yeah.
But then there's others on my face the way around 1, 2, 3. You know what I mean?
Yep. Okay.
It confuses me. And then I get them wrong, and then I'm
Okay. So when we start talking about naming again, so when we get back, we'll take a 5-minute break. So we were talking about nomenclature, right? So I told you, I said, in the case of where we have other functional groups. So here's an example of another functional group, right? So although this has a longer chain, the double bond has priority. So the double bond gets the last name, okay? So the one that has priority gets their last name, okay? So what do I mean by that? That means it goes to the end. So for instance, this guy is 1, 2, 3, 4, 5 carbons, where this guy is only 4 carbons, right? So we're not going with the longest chain in this context. We're going with the one that has the double bond. So this guy is called 4-penthoxy 1-butene, sorry. Okay, where the double bond again is located on the first carbon. Okay, you guys, you clear with that? Okay, and then here is the example, kind of like what we just talked about, right? The one that we just did. Okay. So questions? Okay, you guys are saying no now. Okay, that's right. Priority. Only if no, that's not it.
I think you have questions.
I think I'm just. Yeah.
Mhm. Priority. So far in terms of priority, what you guys know, ethers are before double bonds, right? So ether, example of an ether, right? So ethers are before double bonds. So these guys are lower in the priority chain. So these guys are even lower than the anes, right? So we have the anes, ethers are down here. The halides, the halide alkanes are even lower. Okay, enes are here. Ines, okay, in terms of priority, okay, lowest priority, higher priority. So if we have a double bond, the double bond has priority. So you want to try to have it in the longest chain. If you have the option of having it in the longest chain. If you don't have the option of having it in the longest chain that you can make with the double bond has priority. Does that make sense? Israel, does that make sense?
Yeah.
Okay. Okay, so let's see. Let's see if you guys, well, I'll show you another example and then I'll give you some problems. Okay. Okay, so here we have 1, 2, 3, 4, 5, 6, 7, 8 hydrocarbons, or 1, 2, 3, 4, 5, 6, 7, 8. Right? Again, here, longest chain possible. Double bond. You want to give your double bond the shortest number if you have an option to do that. Okay. And then, because we could have went the other way, right? And it'll be on the third carbon. So you want to give that double bond the shortest one possible if you can. Okay. So if you notice, substituents are state in alphabetical order, which you guys already knew, right? Okay. And then you want to try to give your double bond the lowest number priority as possible, right? If you can't, if there are things that happened before, then you just can't avoid it, right? So, but since you have an option here, 3 versus 3, right? So then you can make this your third carbon chain, your third carbon in the chain, okay? So here we gave our double bond priority. We started with the double bond, giving it the lowest number possible. right? So that's 1, 2, 3, 4, 5, 6, 7 versus 1, 2, 3, right? Does that make sense? Yeah. And if it doesn't, ask. Yeah, that paper. So let me number it the other way so you can see it. Right? So if I numbered here, that's 1, 2, 3, 4. Right? This will give my bromine a low number, right? But double bond has priority. We want to try to give it the lowest number. Okay. So that's the reason I start here, numbering here, rather than starting numbering on the other side.
So wherever a double bond is, that's what we start. We wanna give ourselves-
Not necessarily. So if the double bond is in the middle, you don't want to start in the middle, right?
But if
That's right. We went on to start
we
it.
wanna start off with
That's right. Yeah. And so there, as you've seen, there are contradictions, right? You've noticed that, right? And so, but it's because those contradictions exist when they're at equal or the same priority, right? So if they both are enes and or YL, base single bonds, they're all at the same priority. Okay. Okay. So if both directions are giving the same number for the functional group, the correct name is the one that has the lowest substituent number, right? And you guys already need that. So in the case if the double bond is in the same spot, then now we look at, okay, so which one has the lowest substitute numbers, right? So this one has a 1, 2. So we start here. 1, 2, 3, 4, 5, 6, 7, 8. Or if we went the other way, that would be 1, 2, 3, 4, 5, 6, 7, 8. Okay. So the green numbers are the ones that we would choose in this case because we'd have 1 at the 2 and 1 at the 5, compared to having 1 at the 4 and 1 at the 7. You understand? And that's only when the double bond, it doesn't matter where you could go with the double bond. Okay. Abby?
yes, I get it. And that goes back to what we were gonna do
That's right.
when you
Exactly.
mentioned about like you always want
That's right. That's right.
that goes with that.
That's right. Okay. This is another example of exactly the same thing. Okay, so let's try a problem. So draw isomers for the compound. And this is your compound. And it has 2 double bonds. How many isomers does this compound have? Name each isomer. Okay, so what are we looking at? Okay, so we know there's 2 double bonds. Okay. So that would be 1. 1 chloro. 2 4 hepta. Right. Okay. Okay, sounds good. Anything else? So are there any isomers? Mhm. Okay, so these guys would be Z's. Okay, so you said 2Z, 4Z, 2Z, 4Z. That sounds so funny. 2Z's, 4Z's. Okay, adjust that. Okay, so that would be 1. Okay, so yeah, we could have our double bonds because either they can be Z's, or no, Z's, or E's, right? So let's do it like this. This is gonna look ugly. Hold on. Oops. Okay. Okay, same name. Only thing now we have 2E, comma 4Z, 1 chloro, 2 4 heptadene. Okay. Okay, so then we could also have the other case where we have 2 E's, and then where we have ZE. Okay. Piece of cake? You guys got it? And you see the distinction, right? So again, in this case, these are enantiomers. You have enantiomers of each other, right? Two sets of enantiomers. Okay. Come on. questions, concerns, Cash? Kool-Aid? Okay. Okay, cyclic alkenes. Is this something we should share? Did you say stressing? Oh, okay. Okay. Like, what are you stressing about? You know, this is that hard. Okay. So we have, in the case of the cyclic alkenes, again, we have options, right? So again, we want to try to get the lowest priority between the two. And then since the double bond has priority, it's gonna have, we're gonna start at it being between the first carbon and the second carbon, right? So here, 1, 2, 3. We next look at the next functional group, right? To do the numbering of our carbon chains, okay? So this guy is 3 ethyl cyclopentene, right? And we don't have to say 1 because we know that it's going to start with 1. Okay? That's the same thing that's here. That's the same thing that's here. So you don't have to put the 1. If you put the 1 there, it's fine. Right? Now, if you have more than 1, then you're going to have to do that, right? Or if you have more than 1, then you're going to have to put the number there. So, okay, you guys understand that? Not too hard. Okay, so this guy, double bond between the 1 and the 2 carbon, and then we do our counting, right? So here, that means that this guy is going to be 1,6-dichlorocyclohexene, and it's not going to be 1, 2, so 2, 3, right? Because we want to, in this case, give both of them the lowest number possible. Make sense? If we can do that. And so this guy would be, instead of starting here at the 2, we'd start them both at the 1, right? 1, 2, 3, 4, 5. So then that's 5-ethyl, 1-methyl cyclohexene. Okay, and here, that's 1, 2, 3, 4, 5. So on the 4th carbon, 1, 2, 3, 4. Okay, on the 4th carbon, 1, 2, 3, 4, 5, 6, 7. Okay, so this guy would give me an octane. This guy would give me a heptene. So which one am I going to go with? Number. So if you look, so the octene, so 4 works out either way. If I go here, this will be our methyl. This here would be our bromine, right? So why is bromo chosen over? Because this would be 2-bromo. This would be 2-methyl if we started from this side. So why do we choose counting in this direction over that direction? Priority. Okay. So bromo has priority over, and also alphabetically, B is less than. Yeah, right? Is that true? Okay. What about here? We have bromo in one direction. We have chloro in the other direction. Which one is going to go first? Why? That's right. Okay. because it gives that methyl group a smaller number. If we went the other way, it would give that methyl group a larger number. So really, it's based upon the methyl. Otherwise, we'd have probably gone with the bromo having the lower number. Does that make sense? So if we start, starting here, 1, 2, 3, right? 4, 5, 6. That gives me a 4 here. If I started here, that'll be 1, 2, 3, 4, 5. So that methyl would have a 4. This methyl would have a 5. If the methyl group wasn't there, then we would go with the bromo because B is lower than C. So we try to give it, and since it's the same both ways, we'd go 1, 2, 3 versus 1, 2, 3. Alphabetically, yeah. B lower than C as an alphabet, yeah. Yeah. Where? In the methyl? Then it would still be the chloro way. Chloro it would go 1, 2, 3, 4, because it has, you understand? So regardless of what's there, because this will give me a lower number overall. Because these numbers are going to be, it's going to be 3 or 6, depending on which way you go. All right. Okay. Okay. So what is the name for the following compound?
Wait a second. Hold on.
Did you like any numbers, your answers? Okay. How many of you guys think it's A? Raise your hand. No A's? Sure. Okay. Any B's as in boy? Any C's as in cat? Any D's as in dog? Any E's? Wait, okay. Was that a C or was that a E? That was a D? Okay. So any E's as in elephant? Did you vote? You voted for C? Okay. And you voted for E? E as an elephant? Okay. So let's talk about it. Where should I start where should my starting carbon be? I have 1 carbon. So right here. So that would be 1. And then 2 would be, this will be my 2. Then I have to follow suit now, right? Okay. So why is that the first carbon? That's right. We get a twofer, right? So the goal is to try to, if we can get twofers, we want twofers, right? So this gives us our twofer. We both start both of these at 1, right? We know that the double bond is going to have priority, right? So we want to make sure that it has 1. Okay, so then this guy would be called D, right? Correct answer is D. That's in donkey. So it's 6 chloro, 1 methyl cyclohexene. You see that? Yeah. Okay. Vinylic and allylic carbons. Okay, so vinylic carbons are going to be the carbons that have our sp2. In other words, double bond, right? So these guys are going to be your double bond. The carbons that are directly attached to the double bond. These carbons are going to be the carbons that are adjacent to the double bond. Okay, so allylic are going to be adjacent to the carbon double bond. Make sense? You guys remember what sp2 means? sp2. Hybridization, that's right. Yep. Oh yeah, this is funny. I have 2 generations of my 1A class. I mean my 1 series class in here. This is interesting. I have the online, mostly online generation, and then I have the face-to-face generation. It's interesting. Okay, so this guy's common name would be vinyl fluoride, because it has a chloride attached to a double bond. Right? This guy would be allybromide. So because the bromide is actually attached to the adjacent. Yes, that's right. Thank you. So, but you notice when we do use the systematic name, this is called chloroethene. This guy is called 3-bromopropene. What was that? Oh, welcome to science. All right. And that's why IUPAC, they've been trying to push that, hey, you guys learn it. The problem is that there's so many people that still use the common names, you know. People don't want to give up. It's kind of like there are still people that believe people of different races shouldn't make babies because, you know, it's a sin or whatever, for whatever reasons, right? Same concept. They're stuck in their ways and they don't want to move to the future. Yes. Yeah. So the vinyl group is just representing the double bond. It's just that double bond, essentially, or the sp2. Okay. Okay, so here's an example. So these guys, this is our vinyl group here, right? So this guy is called vinyl cyclohexane. This guy is our ally group. So this guy is called ally cyclohexane. This guy is called methylene. It's a methylene group. So this guy we call methylene cyclohexane. This guy is chloromethyl. This guy is called chloromethyl cyclohexane. Okay. Again, these would all be common names. This, yeah, you're going to have to be familiar with it. It's all multiple gas, so you should know it. Okay, so you guys know that in the case of the double bond, one of the bonds is going to be a sigma bond and one of the bond is going to be a pi bond. This represents the pi bond, so that's the bipon overlap. That here represents the sigma bond. So pi bonds are here, right? And then you have the sigma bond as well. Okay. You guys remember that? Where a double bond represents a sigma and a pi. What was that? Way back in the day. Okay. So, was that a question or was that just scratching your nose? Okay. Okay, so in this case, the 6 atoms of the alkanes are all going to be on the same plane. So we know that this guy is going to be, it's not going to have a wedge type structure, right? So it's all same plane, right? Because wedge would mean you have something coming out towards you, something going up, something. Make sense? So this guy is planar, right? We know that this guy would be, this carbon here is, what would be the structure? Reattachments. Mm-hmm. Mm-hmm. No, not the name of the structure, but name of the shape. Sorry, the geometric structure. What would be
Trigonal,
trigonal? What?
planar.
Trigonal planar. So each of the carbons are trigonal planar. So they're all going to sit in the same plane. Make sense? Okay. Yeah? Okay. So you guys remember that, right? Okay. So this gets us back to the question that we just did, right? So this is an example of that same problem. So we have we have stereoisomers of the compound. We have, in this case, for the 2 double bonds, right? So we have a ZZ, we have a ZE, we have a EZ, and we have an EE, right? So which ones are enantiomers of each other? Which ones are the enantiomers? And which ones are the diastereomers? Diastereomers. What do you mean by top and bottom? This one? Okay. Those are enantiomers of each other? You're saying these two? Are you sure? Disagree? You're saying the top one and this one. So we'll say call this A, call this B. Mm-hmm. Okay. So these guys, this is your enantiomer, and these 2 are enantiomers, right? Okay. And then these 2 are diastereomers. These two are diastereomers. Okay. The easy, yeah. Yes. I am recording this lecture. You're gonna have to look at it again. Are you falling asleep in it? Zoning out. Okay, zone back in. Okay, so let's talk about reactions. Now, the best way of memorizing these is to flashcards, right? That's why we bought them for you guys. And I believe they're in order of reactions. Okay. So it's really easy to sit there, especially this semester. A lot of your reactions, when you see a double bond, right? Double bond is going to be a primary target for being broken, right? So in this case, it's pretty easy. So you're going to break the double bond. If you break the double bond, it's going to have to get an H from somewhere. And in this case, it's going to have a bromine, right? So in this case, this guy doesn't require a catalyst, right? It just requires itself. So just by having, what is that acid called? What was it? Hydrobromic acid. So hydrobromic acid, just by having hydrobromic acid, we're able to sit there and cause the breaking of this bond, right? We don't need a catalyst to help us out. Okay. So, in this case, exactly the same thing is going to happen. It's going to target that double bond. Okay. So it's going to be providing these double bonds are going to be providing the target for the hydrogen and the bromine to sit there and attack. Mm-hmm. That's right. That's right. Now, although it has options, right? It does have options because, you know, it could interact here with the OH group, right? But that double bond is going to be a priority. It's going to attack the first, right? With enough of the acid, you can attack the other. And so if you have extremely excess amounts of the acid, it could actually affect this, and then you can end up with the water or whatever. So, okay. But its primary target is going to be that double bond. Okay. And that's why organic chemistry is kind of fun because like you have different targets, right? So if you're not careful, you overshoot, right? You add too much of one thing, you could end up causing some other reaction to occur as well. Okay. You guys are good. And so often what we end up having to do is we have to do purification to isolate the target that we're looking at, right? So because you end up with a mixture of components. What do you mean? But what do you mean by in terms of priority? Oh, in terms of the, no, it isn't. It just depends, right? It depends on the circumstances because you have that SP. That SP is going to be a prime target for certain things. Other things is not going to be a prime target for. Where the carboxyl, you guys remember what a carboxyl looked like? Carboxyl component could be a target, or the carbonyl. Carbonyl is the double bond in the O. That could be a target of other things, right? So it really just depends on what we're working on. That's why it's going to be important that you guys memorize those things. I know you're fighting it. You guys have been fighting it the whole time. I know. I see it every time because today we didn't go over isomers, and I'm like, yeah. And I'm like, I'm pretty sure we did. And I'm like, I had to think about it. I'm like, oh, what was that? Racemeric instead of racemers, but you should be able, you know, yeah. So, yeah. Well, okay. I see what you're saying. I'm not gonna argue too much with you. Okay. What was that? It was cold, really cold, right? Okay, so I can't see crap. eyes are shiny. I feel like my eyes are just getting better. Okay, so these guys have been organized in 4 different groups, right? And groups are gonna behave similarly in terms of reactions. Okay, so if they're in the same group, these guys are gonna react very similarly. Okay, so in the case where we have a double bond, a triple bond, and you have carbons, extended carbons on both sides, and then if we have double bond, and then we have carbons on the outside. So all these guys are all going to behave very similarly in terms of reactions. Okay, where these guys, if you have these are representing either any halide. The X represents going to be representing a halide, not metals or anything like that. Okay, so these guys and the OHs and the OR represent. You guys know that R is just generic for hydrocarbons, right? Okay, so I just want to be sure that you guys understand that. The OR, this is an epoxy. This is called epoxy when you have O bonded to a carbon bonded to another carbon, which are bonded to each other, right? Those are epoxies, okay? So all of these guys are going to behave very similarly when they react. All of these guys are going to behave very similarly when they react. And then here, this is where Z is either a carbon or a hydrogen. These are when Z is more electronegative than carbon. So it's like nitrogen, chlorine or fluorine or bromine. Okay. And then these guys are all going to behave very similarly as well. Okay. You guys are okay so far? Yes. Hydrocarbons, yeah. And X's are typically used for halides. Z's are going to be used for anything that has electronegativity, essentially, right? Yeah, Z's are going to be electronegative. Moieties. Yep. And then these Z's are more electronegative than carbon. This means that it's carbon or hydrogen. They shouldn't use Z here, but that's what they're going to use. Okay. It's interesting that they don't have. Typically, what they mean by this one is like if they have an R. So you could actually have hydrocarbons here as well too. So it could be an R, a C, or just an H. Okay. Electrophiles. Electrophiles, these are examples of electrophiles. These, they're positively charged. They either have a partial positive charge, a positive charge, or they have incomplete octets. Okay. So, and these are just examples. So H+, this is the ethylene ion. I'm sorry, ethylene ion. Okay, so this is boron trihydride, right? And then that is our bromic acid, right? Or in this case, this is bromine gas. So this is bromine. So hydrobromine, hydrogen bromine. Oh, hydrogen bromide, thank you. Not bromine, thank you. Old age, you know. Okay, so these guys are nucleophiles. So nucleophiles are going to be negatively charged. They're going to be lone pairs, or they're going to be pi bonds, double bonds. Okay, so These guys, negatively charged. These guys, this guy has lone pairs, lone pairs, lone pairs. Then these guys, a double bond, pi bond, right? So also a triple bond will work here too, because triple bond has 2 pi bonds. Okay. So electrophile, nucleophile. You guys see the distinction between the two? Okay. How are we doing on time? 3:56. It's time, in other words. Okay. So no, I want to go one more thing before we go. Okay. So the way it works is nucleophiles will react with electrophiles. Okay. This guy's our nucleophile. This guy's our electrophile. Where is it going to attack? The double bond. Okay. So the first thing that happens is that this is a partially positive, so then it becomes positive. So we throw that H on there. That makes this guy, that makes this guy positive, right? So then we get this guy, well, we attack at this guy, it breaks up the bond, this guy becomes positive. So this guy now is positive, so it's going to interact with that negative, and then we get a bond actually broken. Okay. So it's a 2-step reaction. First, yes. 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 So that positive, that partial positive is going to bond first, right? And then it's going to disrupt the double bond in this guy because it's going to steal that other electron to make that happen. This guy becomes positive. So then this guy becomes the electrophile. And then you still have a negative charged moiety. And then that's going to act as a nucleophile. And then that's going to do the second part of the bond. Okay. Okay, questions. I have a question for you. Which of the following are nucleophiles? So 1, 2, 3, or 4, or all of the above. Nucleophiles. E is correct, all of the above, because we know that 1 and 3 have 2 pi bonds, and then 2 and 3 have 2 is partially, what is that? 2 and 3, well, 3 has a negative charge, so it's negatively charged, and then 3 is also, is that a pi bond? I think. No, it's not a pi bond, but it has that nitrogen in it. It's electronegative. Or 2. Yeah. The lone pair electrons. There we go. What was that? I know. It's been a long day. And I actually, I did have coffee, but it was late. What was that? I have another class. Okay, questions, concerns, Cash, yes. 1 has a pi bond. 4 has a pi bond. Did I say 3? 4 has a pi bond as well. 1 and 4 have pi bonds. 3 is negatively charged. And then, and also 2 has lone pairs. So it is prime targeting. So negative charge pi bonds are lone pairs, nucleophiles. Electrophiles are positively charged, incomplete octet, and partially positive. So This is kind of cool because it only uses that H for the partially positive.